Okay. Thank you, everybody, for joining us today. We have a great guest speaker that's going to talk about Lakehouse solutions to data problems, Alex Merced. And he is co-author of a book, Apache Iceberg, the definitive guide. And if you have not been playing around out there in the data pipeline and data management world, Iceberg is a new, it's not that new, but it's a hot topic. It's seemingly recently gotten a lot of new interest. He is a senior tech evangelist at Dremio, and you can see his LinkedIn web address here on the site. So if you'd like to try and connect with him, please reach out to him there. Alex?
Okay. Hey, everybody. Welcome. Let's see here. Let me share my screen. And here we go. And cool. Can everyone see the title slide?
Yes. Good to go.
Awesome. Well, hey, everybody. My name is Alex Merced. I'm a senior tech evangelist here at Dremio, the data lakehouse platform. We'll talk more about that later. But here, what I'm talking about is lakehouse solutions to data problems, talking about sort of what kind of problems does data lakehouse architecture do? What is data lakehouse architecture? And again, being a data science meetup, think of this as understanding the benefit of data lakehouse architecture to the data scientist is going to be basically getting better access to the data, more self-service access to data, making it easier to execute sort of data quality type pipelines and all sorts of things. So that way you get access to data faster, better data, and easier to access data. So let's get into it. And first, here I have a QR code for all the slides. So that way I'm going to have a lot of QR codes throughout the slides with links to different exercises and things like that. So the easiest thing to do is you can just download the whole slide deck. And actually this will take you to a folder where I have slide decks for many of my presentations. So you get to see slides that I've done in other presentations as well. So I'll bring this up again at the end, but this QR code will take you to where you can find the slides for this particular presentation. Okay. And also, if you enjoy this conversation about the data lakehouse, there's actually a whole conference about data lakehouses, which you can attend virtually for free. We actually do also have a live portion that's in New York. But bottom line, it's our annual subsurface conference, which is going to be May 2nd and 3rd. You can register for free, attend the parts that you can. But by registering, you do get a free copy of Apache Iceberg, the definitive guide. Not the early release copy now, that's going to be, Subsurface will be the release of the final book. Okay, so it's a new book from O'Reilly. O'Reilly's the publisher. I'm one of the co-authors, and you'll get the whole book as a PDF just for registering for the Subsurface Lakehouse conference. And yeah, that was basically my entire 2023 writing that thing. So it's kind of weird to kind of hear that it's finally going to be released. But again, I'm a senior tech evangelist here at Dremio. I've worked in the web and data spaces, doing all sorts of different types of web development tasks, data management tasks, helping people offload different workloads from different sort of CMSs and databases to end up having some more efficient data management, things like that. Now I work with Dremio, basically evangelizing the Lakehouse, Apache Iceberg, Nessie, many of the things I'm going to talk about today, because they're really cool technologies and just really excited to talk about them. So I'm really happy to be part of the Dremio team and being able to get to advocate for some really cool stuff. I'm also the host of several podcasts. All these podcasts are available on iTunes and Spotify. As you can see in my background, I have Gnarly Data Waves. That's the Dremio regular webinars series that we do. That's also a podcast. And then I have In the Grand Scheme of Things, where I talk about data modeling, Data Nation, where I just talk about any kind of data topic that I like to talk about, and then Select Star from Data Lake, which is more data lakehouse centric. You can find all these links over here at bio.alexmerced.com/data, along with my links to LinkedIn, Twitter, etc. I try to keep very busy putting out a lot of blogs, speaking at a lot of events, and doing a lot of video content, most of it being tutorials, hands-on type exercises to help people get hands-on with these technologies and kind of really see the benefits firsthand. Now, throughout the presentation, if you have any questions about any of the content, feel free to put them in the chat. I'll get to the questions at the end, but that way they're there, and then I can scroll through them and answer them at the end. But if we're going to be talking about data lakehouse solutions to data lakehouse problems, we probably should first talk about, well, what is a data lakehouse? So to understand what a data lakehouse is, we need to understand what came before. Okay, so traditionally, and still for the most part to these days, we use traditional data systems, which come in the form of databases and data warehouses. And these are basically bits of software that abstract many things for us so we don't have to worry about them. they abstract away how the data is stored. Okay, so when I put data in Postgres, when I put data in like a data warehouse like Snowflake, I don't really have to think about how that data is stored. It just gets stored in some sort of format somewhere. It's abstracted away. Now, how does the database, how does Postgres know which data is part of which table, and vice versa for a data warehouse? Well, they have some sort of underlying table format. So that abstraction is, again, abstracted away. I don't have to think about that. I just know that there's tables in my database or data warehouse. Catalog, how do I know all the different tables that I have? So there's one thing is to recognize one table, but how do I recognize all the tables and see, hey, I have these 10 tables, these 20 tables, these 100 tables in my database or data warehouse? The cataloging of these tables is also abstracted away. Okay, and this is sort of the interface for me to be able to recognize the data in that sort of traditional table way, but then I'm going to be able to ask questions of that data, being able to process queries, meaning I be able to write SQL, that SQL gets parsed, then a query plan gets put together, and then that query plan gets executed. Again, how all this stuff happens, I don't necessarily have to think about it. I just use Postgres, I just use Snowflake, and it works. The problem is that because it's abstracted away, the data that I have stored in these systems are kind of stuck in these systems. And basically which means they also inherit all the limitations of those systems. So, not every tool, every database, every data warehouse has features for every use case and workload that I need to do. So the problem happens is that now I might need multiple tools to achieve sort of different use cases. And now I have to start moving my data into different systems, creating multiple copies, which introduce costs in the case of storage and the compute to do these data movements. It introduces, additional data copies, which become hard to sort of maintain and sync for regulatory purposes. It introduces a lot of challenges that on a smaller scale may not be too much of a challenge, but as you start getting into larger, hundreds of terabytes, petabyte scale data, these challenges become really pronounced. So it's time to kind of think, hey, is there another way we can architect our data so that way we can have that data available for all our use cases without necessarily having to create so many copies and without so much cost? Okay, and again, databases typically being for like operational type workloads, which may be more row-based type structures, and data warehouse typically for analytics, oftentimes columnar type structured data. But we do have somewhere that's kind of like a universal access place for data. We have something called the data lake, where we just take some sort of storage layer. This could be like a Hadoop cluster or an object storage like an S3 or Azure's ADLS, and we can just store a bunch of data files, CSV files, JSON files, Parquet files, ORC files, whatever files we want to access our data in. And then we could use tools that are basically designed to access that data. These will be compute or processing tools like Dremio or AWS's Athena that can go read those files, run SQL against those files. And that's all fun and good, but it's generally oftentimes read only because those intermediate abstractions aren't there. Like basically, there isn't a way for me to necessarily automatically know, hey, which groups of Parquet files are a table, or hey, how many different tables do I have in this storage layer? It's just storage. It's just basically a large distributed hard drive. So in order to kind of allow us to treat that data lake as our main data warehouse, main database, we need to introduce those abstractions, those intermediate layers that are missing. And that's where the data lakehouse architecture comes in. We still keep our storage layer, so my data would still be stored on Hadoop or still be stored in S3 or ADLS. I can still use tools like Dremio and AWS Athena to run queries against that data. But now we're going to introduce a table format. This could be something like an Apache Iceberg, a Delta Lake, Apache Hoodie, and then a catalog to track those tables. And particularly, I'll be talking about Nessie today. Okay, and once we have all this, technically you now have all the modular pieces that allows you to have this sort of open database or data warehouse. That's the term data lakehouse, because you've turned your data lake into a data warehouse. You can now you have all the asset guarantees you would have in a data warehouse. You're able to do a lot of things like time travel, being able to query historical versions of your data, much more easily do things like partitioning and really have a really nice SQL-centric focus and access to your data, and have consistently defined data sets thanks to these additional layers. So Now I can have my data in one place. I don't have to keep making copies of it for every use case, which is going to reduce my cost of storage, reduce my cost in compute because I'm not writing as many pipelines to keep duplicating the data. And basically different tools. So I might be wanting to do some of my analytics with Dremio to run like SQL-based analytics. But then there's another tool called PuppyGraph that, hey, if I want to take those same tables and run them as a graph, I can do that. I can use PuppyGraph, load up the same Iceberg tables, and run graph queries using like Cypher or Gremlin graph languages to run queries as a graph against that same data. So it allows me to, or then I can use other tools for streaming. I could use like a platform like an Upsolver to stream data in there from like a Kafka stream. So the bottom line is I'm not stuck with like one set of tools. I can find the tools I need for the particular workload I need on one copy of the data. And that's sort of the beauty of data lakehouse architecture. So all we're doing is essentially creating a deconstructed data warehouse with pieces that can be swapped out as needed to meet my needs using open formats that many tools can access. Cool. So now we know what a data lakehouse is. One of those pieces that I mentioned, those intermediate pieces that we had to add in there, was a table format. And one of the hottest table formats out there right now is Apache Iceberg. And one of the reasons why it's become as hot as it is because it's not really particularly sort of like owned or controlled by any particular company. And it's really pretty easy to use. So basically vendors have really kind of rallied around this as sort of like the way that sort of like the neutral playground that we can all share data and work with data interchangeably with on the data lake, more and more so. But what is it? Like, how does it work? Because all the table format is, it's not the actual data. So at the end of the day, typically for analytical type data, ideally you're storing the actual data as Parquet files. Okay, and Parquet files, another Apache project, is just a table format. It's a data file format that you would basically, instead of saving the data in text like CSV and JSON, you would save them in Parquet files, which is a binary format that's columnar. So it's going to be better for analytical workloads, but it also has its own metadata within the file that allows tools like Dremio to scan that file very efficiently. So we're not going to change that. Your data will still be in Parquet. What Iceberg does is that when you might have like a petabyte size table. So all that data is not going to be in one Parquet file. It might be across 1,000 Parquet files. So basically all that Parquet metadata doesn't really help you because each Parquet file isn't aware of all the other ones. So the idea is we're interjecting this metadata layer on top of all the files that allows a system like Dremio to recognize those 1,000 files as a single table and have metadata about all those files in aggregate to be able to effectively scan it. So the way it would work is that a query engine, again, like a Dremio or AWS Athena and many other engines that support Iceberg, they would consult your catalog. Okay, and there's lots of things you can use as your Iceberg catalog. Okay, and basically the catalog does what you think it would do. It lists the different tables. It says, hey, here's table A, here's table B, here's table C. And it basically stores a reference to where you can find the metadata for that particular table in your storage. So all the actual metadata are actually just files in your storage, JSON files, Avro files. So if I'm Dremio, I would consult one of these catalogs. I'd say, hey, I'm looking for table A. And that catalog would say, hey, the metadata for table A is located in this address. So it's in v2.metadata.json. Okay. So essentially what happens is that there's these files called metadata.json that actually have sort of the definition of the table. They carry like the schema, how the table is partitioned, the list of snapshots for the table, all that kind of data is here. And every time the table changes, you create a new metadata.json. So, hey, when the table was created, we had v1. The next time we added some, added some records to the table was v2. Then the next change is v3, and the next change is v4. And basically what happens is that the catalog is always pointing to the newest one. Okay, so the idea is at the end of every transaction, we update the catalog and say, hey, here's the new metadata file. So that way, Dremio and any other engine will always find its way to a consistent definition of the table. We're always being pointed to the latest, greatest version. Okay, now from this metadata file, what I would do is I would scan, hey, this is what the schema of the table is. So that way I can superimpose that schema on any data files, how it's partitioned, and just kind of gather all this information. And then I figure out, hey, which snapshot, like which version of the table am I scanning? So let's just assume we're scanning the most current or the most up-to-date version of the table. So in that metadata.json file, we'd find a reference to the manifest list for that snapshot. Okay, we'll talk more about that in a second. So each snapshot gets its own manifest list. Okay. And what a manifest list is, it's a list of manifests. And this is where the terminology is a little tricky. So I'm going to just skip to the next piece real quick, just to kind of point this out. So what happens is that every time we say, hey, there's a group of Parquet files that make up a chunk of the table, that makes up one manifest. They're usually separated by partition. So each partition may get one or more manifests. So let's say we have a table of voter data that's partitioned by, political party. There might be one manifest file for all the Green Party people, for all the Blue Party people, for all the Red Party people, for all the Yellow Party people. And it would list all the individual files that have those particular entries. And then the manifest list would list the manifests. And the reason it's done this way is to help scan it efficiently. Because what can happen here is that if, let's say it's a partition, like I'm scanning, hey, I only want people who are in X party. Well, I can scan those manifests. Like here's going to have the metadata for each individual manifest, which has stats on, hey, what partition it covers. So I can say, hey, this manifest doesn't cover the data I need. This manifest doesn't cover data I need. This manifest doesn't cover data I need. So that way I don't have to scan all of them. So that saves me a whole lot of time, because the less files I end up scanning, the faster the query is going to be. So basically we'll do that. And then after I determine which manifests I need to scan, I can go to the individual manifest, which is a list of files. So those list the individual Parquet files that make up the table with the same kind of aggregate stats there. So I can say, hey, this particular Parquet file only covers values between X and Y for this column. And this Parquet file only covers values between X and Y for this column. And I can determine, hey, I don't need to scan this Parquet file. I don't need to scan this Parquet file, etc. So the end result is that now a query engine can go in there, take a look at a table that's made up of 1,000 Parquet files, and determine, hey, I only need to scan 5 of those files to complete this particular query, resulting in really, really fast scans of the data. Okay, allowing you to have data warehouse-like performance, but with the data on your data lake, which means, again, no need to make all these multiple copies of data. And this is why even data warehouses are now embracing this, because they do realize it's the future. So now pretty much every major data warehouse, Snowflake, Redshift, Synapse, they're all building functionality to be able to read these data lake table formats, realizing that many people really just want to have this architecture. They don't want to be having multiple copies of the data and the big sort of costs that come with them. So they're building in that functionality so that way people still at least use them as a query engine and query the data on their data lake. And so that's sort of like the big thing right now. Everyone's kind of competing over who defines who's going to be the key or most robust platform for doing this kind of work on this kind of data. But at the end of the day, these manifests point to the data files in storage, and we scan those files. So that's how Iceberg mechanically works. It's just a bunch of metadata that allows an engine to more efficiently plan a query and plan what files to scan ahead of time for much more efficient, much more faster querying, which also, again, has a bunch of other benefits like time travel and so forth. But again, we need to catalog those tables. And most Iceberg catalogs, they're just catalogs. They track your tables and they track the reference to the tables, but that's it. So you can use Hive. You can use AWS Glue, which is just essentially managed Hive, managed by AWS. And there's others. But Nessie is an open source catalog solution that was created specifically with Iceberg in mind and provides something really unique. It provides Git-like versioning at the catalog level, which allows you to get a lot of the benefits you would get out of Git for code, but with your data. Okay. And the way this works is that essentially, again, a query comes in from a query engine like Dremio, and then Dremio would consult the catalog. So in this case, a Nessie catalog, and say, hey, I'm looking to, I'm looking for table A. And again, Nessie is going to have a listing of each table and sort of the reference to that snapshot. So in this case, but the difference is that every time those snapshots change, Nessie doesn't just change it and then forgets the history. Nessie is actually tracking its own catalog level history. So there's catalog level commits that are taking snapshots of what the references are pointing to. So in this case, right now, table A, table B, table C are all pointing to their first snapshot. So let's say we change a table. Okay, we make a change to table B. So now this new commit is pointing to snapshot 2 of table B. Wonderful. And basically that allows me to time travel the catalog, not just the individual table. So I can actually say, hey, I want to run an SQL query against this commit. And then I'll use this version of the tables to run those queries against. On top of it, I can do branches, kind of like you can do with Git. So I can say, hey, you know what? I'm going to make some changes. Like I'm going to be ingesting some data, some new data, but I don't want that data immediately visible to all my end users because I want to make sure I validate, I clean that data, do all that kind of stuff. So I can create a branch. So here I create a branch and then I make some changes. So first I change table A. So we see table A has gone to snapshot 2. Then I change table B again, and you can see that table B has gone to snapshot 3. And I can then run queries to kind of validate, check if there's any nulls, make sure there's no like duplicates, do all my cleanup work. And then once I feel like the data is ready to go and ready to be published, I can publish all those changes simultaneously by merging that commit in. Okay, just like we would do with Git, but with our data. And this gives us a multi-table consistency where basically if I have changes across multiple tables, I can isolate all of them and publish them all at the same time. Okay, on top of that, I can actually tag certain commits. So I can actually give a name to certain commits. So that way, if I need to replicate, like, hey, here's our end of month snapshot. So that way people can always consistently query the end of month data because we've given a particular commit the end of month tag. We can always make sure that, hey, when we're doing these temporal comparisons, we're doing it against sort of consistently things because we tagged the particular point in time we want to reproduce as our sort of benchmarks. And it adds all this kind of functionality into how you work with your data. Okay. Now, again, the benefits of this are you get to isolate the work you're doing on your data. You can actually create branches, which like Git doesn't copy your code. It creates essentially a alternative changes to your code without actually duplicating the files. So basically a zero copy environment, which can be used for experimentation. Like actually going back to that zero copy thing for a moment, a really interesting use case I've seen with a customer is they are a financial institution and they have to run like stress tests every day on their data for regulatory purposes. And usually this would require them to make a duplicate of all their data then they'd have to make all these changes for these like different scenarios to that data, run the queries to see, hey, run those stress tests, scenarios, and then they'd have to dump that environment at the end of the day. So you'd end up having these huge sort of duplication and storage costs that would go with having to comply with this. Now with this, they can just create a branch. They can just create a branch at the beginning of the day, make changes within that branch without duplicating the original set of data, run all their experimental queries in a way that's isolated from everybody else. So the pristine production data is still what everybody else is querying. Once they're done running all their stress tests, they can just dump the branch and then all those extra files get cleaned up on the next cleanup operation. Making it, again, a lot lower cost to kind of maintain and make sure they're complying with the regulations they need to comply with. Multi-table consistency, we already talked about that. You can make changes across multiple tables because there is table level versioning in Iceberg. But again, that's only per table. Since you're capturing these changes at the catalog level with Nessie, you can do multi-table semantics. Like I can roll back multiple tables by rolling back the whole catalog. I can query the entire catalog as it was, instead of having to say this table at this snapshot, this table at this snapshot, this table at this snapshot, I can say, hey, query all these tables, but the catalog is at this point in time, making it much simpler to do those time traveling across multiple tables, things like that. And I already mentioned rollbacks, again, reproducibility through tags, and then the ability to isolate your validation. And Nessie specifically, again, it's catalog level, which is what enables a lot of that multi-level, multi-table semantics. It's open source, so you don't need to use a vendor to use. You can just stand up your own Nessie server, and you can do it self-managed. There's a Kubernetes Helm chart, Docker container, pretty easy to stand up. I have lots of tutorials where you can, and I'll share some at the end, where you can actually literally stand up a whole Lakehouse on your laptop, just to kind of see it, in this and how easy it is to create a Lakehouse environment, in a microcosm to actually kind of get hands-on with it. But it's open source. There is a managed service. So we at Dremio, we do have it integrated into our cloud service. So basically when you're using Dremio Cloud, the catalog in Dremio is Nessie. So you have all those branching, merging features just integrated into how Dremio works. It's cloud agnostic. So again, it's just regardless of how you're using it, whether it's self-managed or managed, you could use it with any cloud you like. And you can use it with private clouds. It's just basically software you can deploy anywhere you like. It's also storage agnostic. It doesn't matter what storage layer you're using. So you can use Hadoop, you can use S3. Okay, there's other solutions out there that provide you file level versioning, but oftentimes they're strictly for S3 compatible storage layers. And Nessie comes with its own optimization tools to help you kind of do garbage cleanup across those branches. So and then on top of that, Dremio packages a lot of that up with additional features for table optimization and stuff like that. So it offers you a lot of benefits to work directly with Nessie as your Iceberg catalog if you're working with Iceberg. So those are two technologies that are really cool, both open source, Apache Iceberg, which allows us to define tables in our data lake. So that way we don't have to be making tables everywhere else. And then be able to use lots of tools with the same copy of the table. We have Nessie that's going to allow us to track those tables. And then again, the catalog becomes the way that different tools discover your tables. So if I'm using like Apache Spark or Apache Flink or Dremio or whatever engine, what they would do is they're really going to communicate with Nessie, and Nessie will tell them where those Apache Iceberg tables exist. And that's generally sort of like the mechanism by how that all works. Okay, so basically the catalog allows us to kind of bundle up all my tables, kind of like in a little basket that I can just take anywhere I want. And basically between those tools, I essentially can, my catalog of tables is no longer attached to a particular query tool. I can use many query tools with it. So one day I can query with AWS Athena, another day with Dremio, another day with PuppyGraph, and so forth, which is a beautiful, beautiful thing. So now we're going to start kind of getting into some sort of like bigger picture problems. So you can see sort of like one, where Iceberg and Nessie fit in, and then how we build a platform around it, and why, how all that's solving a lot of problems that make things a lot easier for everybody. So if we take a look at sort of like the way things kind of work in the world right now, what happens? You have lots of data sources, lots of databases. You might have event streams coming in through Kafka. You might have like IoT sensor data coming in. You have data, and then that's structured and unstructured. And the problem is you can't really store unstructured data in a data warehouse. So typically you dump all your data first in a data lake. Okay, so that way you can store at least a central place for a copy of all your structured and unstructured data. Okay, and then the data engineers, they're writing all these data pipelines to get that data from point A to point B. And it's usually not just like one batch of code. There's like lots of them, and there's lots of them that are interdependent in Python and SQL using lots of different tools. And not only do they have to write this code, but they have to test this code, then deploy this code, and then maintain it. So it becomes a lot of work just to get that initial sort of movement going. And it also gets really expensive when you think of sort of all the computing, all the storage costs, and so forth. But usually, traditionally, we don't do a lot of our like BI dashboards, reporting, and whatnot directly from the data lake. So we end up ETLing, again, that data, a lot of it into a data warehouse. It's like, oh, and that means more pipelines, more of those complex layers that have to be written, deployed, tested, maintained, and all the costs that come along. And on top of it, here, you're going to hit a bunch of egress costs, because oftentimes when you're moving data from your S3 or your cloud object storage, there's a cost to taking the data out of that and moving into a different network. So when you're moving your data from your data lake to your data warehouse, you're paying for the compute, you're paying for additional storage, which is more expensive in the data warehouse, and you're paying for that egress cost and that data movement, which oftentimes catches people off guard when they see the size of those bills. Okay, yay, data warehouse invoices. So bottom line is like, and then again, to a certain scale, at a certain point, that works fine. The cost is fine, but you start getting to a point where it doesn't. And the complexity just gets kind of, now the complexity is not only expensive, but it's slowing things down. Okay. I don't know how many can relate to being in a situation where you're working on a model, you have certain data that's accessible to you, but then you realize that there's a certain feature you want to add to your model. The problem is the feature is not accessible in the data that you have. So you have to put in a request, data engineering, to say, hey, can you add this column? And now it takes them, which should be really simple, takes them like 3 weeks, because there's so many different steps to get that part of the data to where you have your data. The more we can kind of trim how many steps it takes from point A to point B, the quicker and more self-serve you can get that additional data accessible to you. And that's sort of the goal here. Okay. And then again, some of that data gets used from data lakes, but again, a lot of it will be from data warehouses. and you have this whole sort of complex machination. And the end result is a lot of those pipelines break. Okay, all it takes is just one line of wrong code, and that whole chain of things break, and you have nulls in your data, duplicates in your data, outliers that should have been caught in your data, all sorts of things that then you have to go fix on the other end. Okay, and that also leads, if 5 different people fix the same data, then you have 5 possibly inconsistent versions of the same data. So you rather have that cleaned up front. So you have these broken pipelines that either slow down the access to the data, because then you just don't have the data at all because it broke. And again, they're all interdependent. So it can be quite tedious to kind of go and backfill this data. And then what happens? Okay, consumers, data analysts, data scientists, they're like, wait a second, I can't do the work I need to do if the data is not there. Okay, what's going on here? This is not good. So they're upset. So if you're that data engineer, this is not a good life. You're spending your weekend backfilling while everyone is mad at you. That's a lot of stress. And again, there's also the cost. So if you're if you're managing all this, and the thing is that ideally, what would you rather do? Like, would you rather be spending all this money on things like storage, the compute costs, the network egress costs, the lost, and then also the cost of the lost productivity because of that, the things that need to be done aren't getting done while you fix these things, the regulatory fees because maybe you've accidentally exposed PII because of a mistake in the code, or data models that drift because mistakes in the data, or changes in the model over time, and just the overall cost of bad insights when you're making bad decisions because the data isn't right. Would you want to rather spend money there, or would you rather be able to grow your team because they can work more efficiently, and you can actually have the additional team to be able to make more data available in a more robust way because your team is building your data platform instead of putting out the fires with maintaining your existing platform. So that's the goal, that's the hope, and that's why that's sort of, again, the hope with the data lakehouse platform. So what you do is, the solution is to build a data lakehouse platform using a lot of the tools that I've talked about so far. But how do you do it? Like, what would be the ideal data lakehouse platform that kind of solves all these problems? What would that look like? If I start thinking about it, it should have access to my data lake, right? It's the data lakehouse, so it should have access to my data lake and be able to access those Iceberg tables and possibly other formats on there. Okay, so an ideal lakehouse platform should be able to read my Iceberg tables on my data lake, whether that's ADLS, S3, Google Cloud, whether it's an on-prem data lake. Okay, and this is where we start getting into the concept of unified analytics, the idea that, hey, we have a place where all my data can kind of coalesce, okay, where I can have this unified semantic layer where I can kind of cache all my metrics and things like that, and also be able to govern access, because that's another big challenge with the way things are. You oftentimes have your data in like a bajillion different places, and I want to, hey, so someone asked me, hey, I need data access to this table. I give them access to the data source, but now I'm governing their access to like 5 different sources, each of them with their own sort of quirks. And that gets really, really complicated. So it'd be nice to have one place where I can determine who has access to what table, what columns, what rows, all from one platform, regardless of where the data lives. So the data can be in Mongo, the data can be in, like a NoSQL database like Mongo. It can be in a SQL database like a Postgres or MySQL. It can be in a data warehouse like Snowflake. But instead of me having to go manage permissions in each layer, there's a single place where I manage permissions, making it much easier for me to audit who has access to what, but also easier for me to grant access. Okay. But then a good data lakehouse platform should not only be able to unify all your data, but it should also allow me to query that data. And not only query that data, but be able to federate queries. So that way I can join a table that's on my data lake and join it with a table that I have in MongoDB. So that way I'm doing all these operations from one place, and I don't have to move the data every time. Because while the way I always think about it is like an 80-20 rule, like probably if you're doing this, 80% of your data should probably be in the data lake. But there's going to be 20% of the data you really don't need to. Like, you might have some data you have from Snowflake because you're getting it from the Snowflake marketplace that you're just using to enrich a data set. You might have some data in MongoDB that, it's just not a major data set, doesn't necessarily really need to be moved. So you just want to be able to join it directly from. So there's going to be about 20% of your data that's going to be in these other long tail of sources. So you want a data lakehouse platform that not only allows you to query your data lake, but allows you to mix that data with this long tail of sources. Okay, and offers good acceleration of those queries. Okay, because what happens in nowadays, oftentimes we get to the data warehouse, if a query is too slow, we're building all these materialized views and BI extracts and cubes, and those are fine. They do the job. The problem is, like, these oftentimes require a lot of maintenance on the side of the data engineer. It also requires additional sort of mental, what's the word I'm looking for? More mileage mentally for the data analyst and the data scientist, because there might be 5 versions of the same table. Okay, and you have to know which version of that table or which materialized view is the one that's optimized for your particular question. So it becomes having to juggle all these different versions of the same data mentally, versus just asking the question you want and letting the platform figure it out. Okay, so a platform that has a feature like reflections that says, hey, we'll make it really easy for the data engineer to create all these different versions of the data, but we're not going to create other additional names. They're not going to look like other tables. It's just one table. And then when the analyst or scientist queries that table, we'll figure out, hey, which of these materializations accelerates that query for you. So that way you're just thinking, hey, this is the table with the data that I need. Let me run what I need to do. And the platform will figure out, hey, which version, which physical data set is the right one that's set up in the right way. So that's pretty cool. So basically, again, an ideal data lakehouse platform should be able to unify all your data, should allow you to query all your data in a fast way with a really ideal. And again, the faster it is, it's not just about how fast the query is, it also means lower costs. Because oftentimes when you're dealing with these platforms, you're dealing with compute that you're getting from a cloud vendor. And if you can spin down that compute faster because your queries run faster, you also save money. Okay. And also other things like caching can help reduce those egress costs and network storage costs. So there's a lot of ways that a really performant query engine can reduce the cost of everything. And again, that cost means you can invest elsewhere in developing your data platform and expanding its reach, expanding its access, investing in things that will give you a return versus maintenance. And an ideal lakehouse platform should help manage your lakehouse. When you use something like Snowflake, one of the reasons why people love cloud data warehouses is because they don't have to manage what's going on under the hood. It's abstracted away. Like, how that data is stored and optimizing that storage is not something you have to think about. Traditionally, in a data lake, you do. Okay, if I have like 1,000 Parquet files on my data lake, and when it comes to things like partitioning skew and compaction because files are too small or they're too big or they're not sorted right, like, it's up to me, the data engineer, to go in there and rewrite these files in a more optimal way. Okay, if I want my lake house to feel like a data warehouse, there should be some mechanism that kind of does that for me in the same way like in a data warehouse. So a good lakehouse platform should be able to take care of that for me. Okay, basically be able to optimize my data so that way it just works. It's just fast. They're just tables that exist that I can query, like when I'm working with a database or a data warehouse. But additionally, give us new cutting edge features like that whole Git for data paradigm, where I can create branches to do sort of more advanced data ops and manage my data quality. Okay, so a platform that has all of this would be sort of ideal. And what kind of platform? That platform should also make that data very accessible. Okay, because people want to connect different BI tools. People want to connect to their Python notebooks. People want to connect their data so that way they can write models. So basically, this platform should be able to deliver that data through the interfaces that people use: ODBC, JDBC, Apache Aeroflight, which is a really fast way to deliver data in a columnar form. I have whole talks just on that topic alone. That's a really interesting topic. Or through a REST API so that we can automate operations in that platform. So you want to have all these interfaces. And basically now, I'm sure you know what the punchline is going to be, but bottom line is, what platform has all these features? Dremio. Yes, I mean, but it is really cool. Like, it actually is. I wake up every day really excited, like knowing that like all this is bundled the way it is, because it is really cool, and I've seen some people do really cool stuff with it. But the cool thing about it, and also what's special about this platform, is that there's different ways to deploy it. Because the problem with a lot of cloud platforms, like the ones that people know, Snowflake, Databricks, they're generally cloud only. So oftentimes, if you are running an on-prem type situation because you have to for regulatory reasons or whatnot, you're kind of locked out of these platforms. But Dremio has a self-managed enterprise edition. So that way, hey, if you need to run it in a sort of, on-prem or within a private cloud, you can do that. But we also have our our managed version, our Dremio cloud managed version that we manage, so that way you get the power of Dremio without all the work of having to maintain that deployment. And then we have some really cool announcements at Subsurface. I'm not going to spoil yet, so if you haven't registered for Subsurface, the keynote's going to be really cool. But so you have flexibility. Like, bottom line is you can deploy it where you need it. If it needs to be on-prem, you can do hybrid lakehouses because it can connect to on-prem and cloud data sources. So you can join your on-prem tables to your cloud tables and so forth, which is a very popular use case. And it's really fast. Like, that's one of the key things. Like I would say, hey, it's the most robust platform that has all these features. But one of the key things that differentiates it from other possible options is going to be like the speed and the way it accelerates data. Because the reflections feature that accelerates data is part of how the query engine works. So you don't have to deploy another thing. Okay, like there's other vendors who will say, hey, we can speed up queries too. But oftentimes you have to actually deploy a whole other software. So it's like you have two things running at the same time. One thing, and then even that thing that you're running is kind of, one, you have to have the enterprise tier. Here you get reflections for free. Like, you can use Dremio for free out of the gate because you can deploy it. The software is free, the community edition, and then you can sign up for Dremio Cloud for free, and you only pay if you want the upgraded stuff. But you can literally do a lot for free. We try to make a lot of people to kind of really begin building the data platforms at as low cost as possible. But you get reflections out of the box, while other platforms, you have to have their enterprise edition to get, and then deploy that separate thing, and it only works for certain sources. Here works with reflections, work with all sources. It comes out of the box, whether even on our free editions, and it works across all your sources. Requires no additional deployments, and it's just really cool. Again, I don't have enough time to get really deep into how reflections work. I have a whole separate presentation I do on that, but it is a really neat idea, and it's really one of the most unique things about the Dremio platform. Okay, but what do you get when you have a lakehouse? Okay, in this case, I'm imagining, hey, if you're using like our particular solution that gives you the benefits we just talked about, but in general, you should see most of these benefits just by implementing a lakehouse in general. Okay, you're going to notice that specifically in this case with Dremio, we can connect all of our data directly to Dremio. This really is going to reduce the amount of pipelines we need, because again, we don't need to move all that data. Okay, we'll move some of that data, and most of it will really just be landing raw data as Iceberg tables in your data lake. And then Dremio can then model it from there virtually. And again, Dremio can read lots of sources. You can use lots of tools, because again, Dremio's catalog is using Nessie. So that means you don't have to use Dremio to do everything. You can connect Apache Spark, you can connect Apache Flink, you can use the tools you like against that catalog. Again, Dremio aims to be an open platform. You can connect your data everywhere. Other tools can connect to your data, through the Dremio platform, and you can deliver that data anywhere. The idea is we are really, really cognizant of trying not to lock you in and not do what other companies do, and creating a platform that kind of basically, we lock you in and then suddenly raise the price. Like, that's like what other people do, or they set it up in a way where your bill kind of disappears later on. So it's really intentionally set to be open, using open source pieces, open architecture, whatnot, from end to end. So again, you're federating queries to your data. So you're really reducing the amount of ETL work you have. You're not duplicating your data, because oftentimes you build just virtual views on top of you. Instead of creating a traditional data mart where you're making several layers of copies, you just do everything virtually. Everything's going to be like layers of views. And then the reflections feature that I mentioned earlier is what comes in to help accelerate that when needed. In this case, again, you're not duplicating your data. You can govern those views. And again, allows just a much more efficient way to sort of deliver the data. And again, reflections just eliminates the need for things like materialize views and cubes and extracts. And another aspect of that is a lot of times that acceleration, especially for like BI dashboards, happens at the BI tool. So you might be using Power BI, and Power BI has acceleration features. The problem with that is, what if you have another team using the same data, but they use Tableau? The acceleration that happens in Power BI doesn't help them when they're using Tableau, and vice versa. Well, with reflections, since it's happening at the Lakehouse platform level, Power BI and Tableau on different teams using the same data, they're both going to benefit from that acceleration. So you're not building two copies of the same sort of materialization, but just one. And that's where like Dremio semantic layer really becomes really, really useful, really helpful, because it really allows you to say, hey, all my tools will get the benefit of the thing I built for this team needed it, but now everyone's going to benefit from it because they're accessing the same data set. So you get really good mileage out of it. Cool. Okay, so again, less pipelines, less backfilling, fresher data sooner. So again, so if you're the data engineer, your life is a little bit less stressful. If you're the data scientist or data analyst, you're thrilled. Okay, you're getting your data quicker, so it's gonna be fresher, more likely to be correct because it's not moving as much. So it's gonna be much easier to diagnose problems. You can isolate the data in branches, that way you can catch those problems before you publish the data. So yay. And again, this is also the cost. So if you're the business owner, the person who owns sort of the budget side of things, again, less copies, less storage, less pipelines, less compute, less data movement, less network costs, less pipelines. Again, you're going to have more fresh data sets, less copies. You can much more easily comply with regulations because it's easier to audit what you have. Less copies, less chances of data models drifting. And fresher data just generally means better insights. So overall, it's a lot of good stuff. And again, it's not like, hey, you just get from point A to point B overnight. It's a process. You slowly transition from traditional infrastructure to this sort of lakehouse architecture, and that's where most people are nowadays. I would say, like, it's still very early on in this sort of transformation. I would say most companies I talk to are in the early stages of designing their implementation, or in the early stages of the actual implementation, where they're moving over like some workloads, seeing it, proving out the concept, seeing the benefits, and then sort of systematically taking chunks of that work and moving it over versus, you don't just pull out what you have and then replace it. It's a more methodical, and then we do offer a lot of help with trying to kind of do that in a very sort of thoughtful way. Now, what makes Dremio particularly unique, again, because there are like Dremio is probably the platform that's been doing this like the longest. Like we've been, if you go back and take a look at like blogs and videos, we've been talking about the Lakehouse for like, and this whole sort of architecture for 2 or 3 years. Over the last year, Iceberg has gotten really big. So now like everybody's jumping on that story. So there's a lot of people now trying to kind of make their pitch in this space, which is fine. You want options. Again, you want competition. It helps, because again, the beauty of data lakehouse architecture is you don't need to use the same tool for everything. And that's why Dremio is architected the way you have. So that way, if you do want to use different tools for different workloads, you can, but Dremio can really be a heart of building that platform. But again, that reflections feature is really where we take something that used to not work and make it work. Because you might have heard this term, data virtualization, which is like the idea of being able to have a platform that connects to all these different data sources and allows you to treat them like one database. That's not a new concept. There's been platforms like Denodo and Trino that allow you to do this, but the problem always has been doing it at scale. Because there comes a point where basically, yeah, I have all my analytical work going to these systems, these sources, but then they're competing against the other queries that are operational. And there's scaling limits and each system is unique. Okay. With Dremio, and this is where Dremio Reflections comes in, because basically, let's say I have a SQL table or SQL Server table that I want to connect. I don't want to move it to my data lake, or at least I don't want to manually move it to my data lake. What I can do is I turn on Reflections, and for the intent and purposes of every data analyst and data scientist, they're just querying the SQL Server table. What they don't see is that Dremio is creating and maintaining a materialization of it on the data lake and swapping that out. So that way you're not crowding out the scalability of that SQL server. That SQL server is not getting this excess hit on this load of ability to kind of handle queries. And then also, because it's an Apache Iceberg table, it's going to scan really quickly and probably be very optimized in the way it's for those analytical queries. So you're going to be like, hey, I can create this really fast, and my SQL server is still handling all the operational stuff just fine. And it's far the way my experience is like I'm just querying that SQL server table. And because it's sort of like Dremio's architecture is really allows you to do that data virtualization along with those data lakehouse patterns at a really large scale. And again, I would say like half, if I remember right, then last I checked, it was like half the Fortune 10 are Dremio customers or Dremio users. And again, it's for a lot of these benefits. And then also, again, there's just the raw performance of Dremio. So another big open source technology that's talked about a lot is Apache Arrow. Okay, now what Apache Arrow is, it's a in-memory columnar format. So in the same way that a Parquet is a file format that stores the data in storage in a columnar way, well, when a tool like Dremio reads that data from the file, it needs to load it up in your computer's memory to process it. So Arrow created a standard really fast columnar way to represent that data. And that actually started out as the in-memory format of Dremio. Like that's actually literally when it first started. What happened is that one of our founders, Jacques Nadeau, and then was trying to figure out this whole columnar format thing for the Dremio product. And then a lot of the ideas that he was having were similar to the ideas that Wes McKinney, creator of Pandas, had. So then they ended up working together to create the standard called Arrow, okay, which was heavily originally sort of the in-memory format. So Dremio has been using Arrow literally from the beginning. Like it was literally built, came out of out of building Dremio. But now it's like the standard of everything. Like now every tool is starting to incorporate Arrow into the way they process data for those speed benefits. And because Dremio has been using it for so long, it's really optimized its ability to process data really quickly using this format. But it's a really interesting space. Like, again, another project that's really transforming a lot of things. Like you have query, like little sort of like a version of DuckDB that's Apache Arrow based. I don't know, maybe not the best analogy, but something called Data Fusion. That's like a thing that's out there now. Right now, they're actually creating like an in-place replacement for Spark, where you can literally swap Spark's query engine with an Apache Arrow based engine called Facebook's creating one that's called Velox, and then the Apache Arrow project is creating one called Comet. So this is transforming a lot of things. And like I think Snowflake has just created like a way of communicating via Arrow with Snowflake. So a lot of this has really become sort of a standard way of representing data in memory and processing data in the data space. And again, it's one of the key reasons why Dremio is able to oftentimes match or be faster than Snowflake operating on your data lake, which is pretty crazy when you think that, hey, without necessarily having control of the whole system like Snowflake does, it's still able to match the performance. That's, yeah, that still just makes me feel warm inside. But that's cool. Okay, just a few more little cool things. This is reflection. So we already talked about reflection. So I won't beat the bush too much on this one. But bottom line is, again, reflections is a really cool feature that has lots of different use cases, where there's accelerating joins, basically preventing you from having to create too many copies of the same data. There's a lot of really cool aspects of how reflections, on top of how fast Dremio just already processes data, can accelerate a lot of workloads. And again, it eliminates the need for BI extracts and materialized views. Okay, and then the third piece that makes Dremio really, really cool is this columnar cloud cache. So you would be running, let's say Dremio Cloud against like S3 compute, and it's accessing your files on S3. Again, not only is there a cost of egress when you move stuff out of network, and again, Dremio would be running within your cloud, so there would be no egress fees because it's running within your cloud network. But there's also like access fees. Every time you send a request to S3, you send enough requests to S3, you begin incurring a cost. So Dremio has the columnar cloud cache. So what it does, it's monitoring how often certain files are being requested from S3 or from whatever object storage you're using. And it'll cache it on the actual nodes of the Dremio cluster. So that way, in that case, so instead of having to constantly send requests to S3, it can use the cache to fulfill those needs, which ends up reducing your bill as well. So again, speeds up queries, so less compute costs, and also reduce the amount of requests to S3, which reduces that part of the bill. So people do see pretty huge drops in their costs when they adopt this architecture. There's we did like Gnarly Data Waves, as you can see in my background, is like our weekly webinar series. Well, it's not weekly anymore, but it's bi-weekly now. But we recently did an episode with like a S&P. So S&P is a customer, Standard & Poor's, and they actually were able to reduce their cost by 50%. That's one example. And then we just put out a white paper that shows different examples of people who reduced their Snowflake costs. I think one customer reduced it 90%. And all the numbers are in the white paper, but it's pretty, these are actual customers who've seen these outcomes. So like I've explained like theoretically why those outcomes should happen, but there is actual evidence that those outcomes do happen. And then there's unlimited scaling. So bottom line is the Dremio cloud platform allows you to really scale up. So you might have seen this with Snowflake, because Snowflake has features like this too, where you have like the different tiered like engines with extra large, small, whatnot. You can say how many engines you want, when they shut off. You can do all that with Dremio to kind of make sure you don't ever use more compute than you really need. So again, a lot of levers to help keep the cost down. So again, to kind of summarize, bottom line is there's a lot of benefits to Lakehouse architecture. And there's some really key open source pieces, Apache Iceberg, which allows us to recognize those tables on a data lakehouse, Nessie, which allows us to catalog those tables. And there's a lot of tools that work with those. Okay. But, at the end of the day, like there is different people who are competing to say, hey, we are the platform to build a data lakehouse on. And I do think there's a strong case to see, hey, Dremio has a lot of features that really make a strong case for it to be that platform that enables a data lakehouse type architecture. And evidence, actually, people who've successfully done it. But at the end of the day, best way to kind of really see what I'm talking about is to get hands-on with it, and try it out yourself. And the beauty of Dremio is it's something you can run in a Docker container. So you can run it for free. Like I actually literally run Dremio on my laptop all the time just to do little workloads on my own personal stuff. Like, because basically I can just connect it to my S3 and then run SQL against Parquet files in my S3 without me having to do really anything. Like I don't have to write like a complex Spark script or anything like that. It's just running, and I just run queries against my data, or I can upload like a CSV file real quick and run SQL against it. It's pretty nice. So if you want to actually try that out, actually try Dremio, Iceberg, Nessie, and see how it kind of all connects in a very easy exercise. Like literally, it's a very, very step-by-step, easy to do that anyone can do it. All it requires you to do is have Docker on your computer. This QR code right here will take you to that exercise. I've actually done 3 new exercises that are on the Dremio blog that allow you to do an end-to-end exercise. So you actually will ingest the data from a database, like either Postgres, Mongo, or SQL Server. You would ingest the data into Iceberg, then take that data from Dremio and then feed it into a BI dashboard with Apache Superset. And actually walks you through the whole step. And you can literally do it in like 20, 30 minutes. So you're literally doing a whole end-to-end data engineering BI dashboard exercise within 20 minutes. It's pretty cool. And they're fun exercises. But that'll take you to one. This is if you want to kind of like explore Dremio more, but that's essentially the deal there. Again, do attend our Data Lakehouse conference, Subsurface. Again, that's May 2nd, May 3rd. That, again, it's not just about Dremio. There's going to be lots of talks just about Iceberg in general, people talking about their different Lakehouse implementations that may or may not be using Dremio. It's really a Lakehouse conference that's about, what is a Lakehouse? Why does it matter? Why should we all care? There are going to be some AI ML talks as well. There's an AI ML track. We're going to have some of you might know who Chip Wen is. She was the founder of a company called Claypot that recently got bought by Voltron. Very popular in the AI ML space. And she'll be talking there. She'll be talking specifically about a technology called IBIS that's creating sort of a universal data frame that you can use across different tools. You could imagine you could use the same data frame syntax against Trino, against Snowflake, and eventually Dremio once we built out our IBIS backend. And basically, instead of having to learn a different data frame API every time you use a different tool. So that's a thing that's there. And then, yeah, now what I'm going to do is I'm just going to go back to that QR code where you can download the slides. So that way anyone who wants to download the slides can. So that way they get all the links. And yeah, that wraps up the presentation. Again, thank you everybody for being here and listening to me talk on a Saturday. It's very appreciated. Yeah, let's go answer some questions. Okay. Ooh, one of my favorite questions. Alex, how did you make those drawings of yourself? Okay, so so you probably saw that in the podcast images. And if any of you guys follow me on LinkedIn, you'll probably see these very regularly. Like I do this a lot as far as creating kind of really eye-catching LinkedIn posts. And the way I do that is a mixture of a couple different things. I mainly use Midjourney. So Midjourney is an AI image generating tool. One of the things I really like about Midjourney is there's a blend feature. So you can take 2 images and blend them together. And then you can then remix it with a prompt. So for over several months, I was taking like different like cartoon images, mixing them with pictures of myself, just trying out different prompts to kind of get them just right, and then remixing them together over and over again. Until now I have like a pretty consistent, like I have like the right ingredients to kind of generate the kind of images that I want after a while. So that's how I do it. Sometimes what I'll do is sometimes I will use ChatGPT. Not usually not to generate images of myself, just because I already got a pretty good routine with Midjourney. But sometimes I'll generate like props. Like maybe I'll generate an image of a whiteboard, and then what I'll do is I'll superimpose one of the cartoons of myself on top of whiteboard, and then I can put like an architectural diagram in that white space to kind of create to do those architectural diagram posts you see very often, but in a more sort of eye-catching way. So I also will do videos and stuff like that. Like I try to be fun with it, because if you can't have fun with data, what can you have fun with? So I try to entertain, educate, and enlighten, and I always appreciate it when people appreciate the pieces. Cool. Next question. Can we get the link for the S&P Dremio use case paper? It's not a paper, but I can show you where to find it. So I'll put the link here in the chat real quick first, and then I'll put it online.
That was mine.
Perfect. Okay, Dremio.com/gnarly Data waves. Okay, so that's the link. Let me open it up myself so that we can show you. So that's going to take you to this page here. This is where we have all the information about our gnarly data waves program. Right now, there's no upcoming episodes because everything's about subsurface right now. So everything is going to be happening at subsurface, then post subsurface, everything will come back to life. But if you go past episodes, it should be one of the more recent ones.
Right.
Tian, oh, yeah.
You passed, yeah, 50%.
No, that's one me. That's me talking about the Snowflake white paper.
Okay.
I think it's this one right here. How S&P is building on Azure Data Lakehouse with Dremio. And that's them talking about their experience where they were able to reduce a lot of, they were actually able to eliminate entire databases because they were able to operate directly from their data lake, which is really cool. Their use case is really interesting. Like a lot, there's also, if we go way back, because I know some of you mentioned being in healthcare or wanted to be in the healthcare space, there's one where Memorial Sloan Kettering talks about their implementation or their architecture, which is also really interesting. That's like a much earlier episode. I think it's gonna be like right around here somewhere, but it's there. You'll see like actually, here, I'll just do this. MSK. Yeah, here we go. Yep, there it is. The episode 19, data management practice, accelerating cancer research with Dremio's data lakehouse, because they were like a perfect use case for Dremio because they had their data in all sorts of different places and they're having trouble sort of getting it to the right place because it was just a lot of locations to maintain. So now they have everything kind of going through Dremio. Everything's kind of governed through Dremio. So now everyone has much easier, and now everyone is onboarded to the Dremio platform, so they can just go find the data sets they need and curate what they need for their models. And it's really accelerated their ability to kind of get a lot of the data they need, so that way they can continue their research. So and then you see that like that's an example again. Yes, of Dremio specifically, but also just Lakehouse architecture in general on the kind of outcomes it can have with companies that are really making important impacts in the world. So there's some cool stuff like that, and we always have we'll have some good stories like that as well at Subsurface. We always like to highlight, especially like those ones that really like, hey, like it actually changed. Like last year we did like TransUnion, who's a customer, and because of them being able to unify all their data, they're able to get access to data when they're doing credit evaluations that they couldn't before. And now they're able to expand who they give access to credit to. And it's really expanded access to credit in certain like in like third world nations and stuff like that, which was a really cool presentation. But yeah, that's sort of the deal there for those who want to check that out. And let me keep going down the questions. Let's see here. Can we get the S&P? Thanks, Alex. Have to run. Well, I guess you can't hear me say thank you, but Brooke, I'm saying thank you. Let's see here. Thanks. Please do the whole presentation on how you do it. Okay, I will probably come out with a video on Midjourney.
Oh, there you go. Yeah, that was in reference to the images.
Yep. I have to find a good way to like.
Yeah, but I have the feeling that you use Midjourney.
Oh yeah, I love Midjourney.
Yeah,
Midjourney is my favorite.
Definitely. Yeah. It has the it has the tracks.
Yeah. It's I always like the results from their best. Yeah. Please. Okay. What would you be the main benefits of a lakehouse if we're in an environment that only has structured data? It depends. Like the way I would say is like you don't always need a lakehouse. Okay. So like I'm an evangelist of lakehouse architecture, but for when you need it. So things that and then again, this specific implementation, the way I was talking about it today, is definitely heavily related to structured data specifically. So in this case, like the way I talked about it today is definitely very leans into people who have a lot of structured data, but also depends like, are you operating beyond the scale of the tools you have? Like some people operate entirely from a SQL server, and that they do their operations and analytics from SQL server. And if they have like a single SQL server that can handle all of it, and they're not exceeding its capacity, then that's probably fine for now. But then what happens when you start having, you exceed this capacity or the ability to scale up a single instance of SQL Server, and now you have 3 or 4 of them, and you're having trouble unifying that data because they don't necessarily talk to each other either. Well, you could and this is another place where like a lot of people use us. They'll connect all their SQL. Like I can think of 1 or 2 customers like this is literally all they do with Dremio. They connect all their SQL Server instances so that way people can join the data across the different SQL Server instances right from and curate their data sets right from Dremio. But I would say if you start having a lot of data in a lot of places and you're starting to see some real bottlenecks as far as delivering the data where it needs to be, a lakehouse architecture makes a lot of sense And if you decide that Iceberg is the way you want a lake house, then making Dremio the heart of it, I think, is smart. Dremio can work with other designs. Like, we do read Delta Lake tables, but oftentimes when we're incorporated in like a Delta Lake situation, we're usually there to help be the BI tool. So like basically, people will have their Delta Lake tables read into Dremio. They'll turn on reflections and build their BI dashboards off of that. But the bulk of their work is still probably being done in Databricks, because they're using Delta Lake, and Databricks is going to be very, very designed to cater towards the Delta Lake solution per se.
Sure.
But also, there's also people who are exploring using Iceberg on Databricks. But again, it depends on what you're trying to do. But I would say the main benefits is making it easier to wrangle data when you have data in a lot of places. Making it, if you want a data lakehouse architecture because you plan on using multiple tools with the same data, that is going to be where this is going to be really helpful in maintaining that and managing that. But again, if basically you have basically you have a database that's your operational database, and you ETL that data into the data lake, and then you ETL that data to Snowflake or something, and it's like very simple, it can help you reduce some of the cost of Snowflake, but that's only if the costs are a problem. Some people don't have Snowflake bills that they're completely happy with. But if you don't, then that's a place where Dremio can help, because Dremio can help offload some of that work, so that way only the things that need to be in Snowflake are being done in Snowflake. So it depends on use. The way I like to think of Dremio is like a Swiss Army knife. If you have a data lake and you're trying to get more value out of it, Dremio can help you get more value out of your data lake. But if your data lake isn't the main piece, it's not something you're really thinking about, hey, how can I get more value out of my data lake? Then it may not be the most immediate thing you need at the moment. Although I do think, I would say more often than not, there's some sort of value to the platform. Once you start having once you start having all these pieces in place, especially if you have a data lake in general, Dremio is going to probably offer some value. And again, the great thing about it is with Dremio Cloud, you only pay for what you use. So like, you set it up. If no one's running any queries, you're not paying for anything. So you set it up. If you need it, you need it. If you don't, you don't. And then we go down to questions. Happy face. Yay. Gotta go. Enjoy the presentation. I know it's probably already left, Jerry, but thank you for coming, Jerry. And I think that's the last question. Any other questions people want to throw out there? I love talking.
There was one slide that showed EL pipelines, and then at the top it says 0 ETL. Can you explain that a little more? I wasn't quite clear on where you really reduce like the ETL or.
Okay, so I would say 0 or low ETL, depends how you execute it. So in that example with like the SQL servers, where you connect the 4 SQL servers directly to Dremio, usually there you're doing no ETL. Like basically Dremio is just querying the SQL servers directly and pushing down queries. So in that case, you're doing 0 ETL. Now another approach is what people would do, like absent Dremio, absent data virtualization, what they'd have to do is still land the data in the data lake and then unify it there, or move it to one of those databases. They have to kind of have it all in one place somewhere. So in this case with Dremio, you can at least only land the raw data in the data lake. So that's what we mean by low ETL, where you just have to do that initial step, and then everything from there is virtually modeled instead of making. So basically, if you traditionally would think of like a gold and a silver layer, instead of the gold and silver layer being an additional copy with the transformations, you have views with the transformations, and then whenever they're not performing, you just turn on reflections.
Okay, thank you. That helps.
No problem. Yeah, no problem. Yeah, I probably should spend a little bit more time there. It's just like I was trying to make sure that I didn't go, go too long, you guys, because I can go forever, but I don't want to bore you either. Cool. Any other questions?
Nope. I'm going to go ahead and stop recording now, and then that way, if there's anybody that's a little shy or doesn't want to be recorded on the YouTube video, they can speak up as well.
Sounds great. Thank you, everybody, for attending. For those who are watching it on YouTube, and make sure to follow me on LinkedIn.